Okay, welcome to the case study for the end of chapter 3. So I wasn't sure what to do as a continuous random variable, and in the end I decided I'm going to have a look at social distancing and how this affects a very simple simulated outbreak. So I thought, the last lecture we looked at simulating random variables, so let's actually use this for something. So I'm going to start with a very simple model, what we call an SIR model. So the idea is that everyone starts as susceptible, that's the S state, and then if they meet someone who's infected and they get the disease, they become infected, and then after a certain amount of time, they become recovered. So for each person I, we have a susceptible, which you denote S, then they're infected for a certain amount of time, and then they're recovered. And I'm going to assume that we have this nice deterministic idea of recovered. So once you get the disease, it takes K days for you to recover, and that is just a fixed amount. But what we're going to do is we're going to have a look. We're going to say that once a person becomes infected, they're going to go out and meet altogether XJ people. And what that means is that it's almost like you choose randomly from a Poisson distribution the number of people you're going to meet. So we're going to have a rate lambda for each person. So you get infected and you basically decide you're going to go and meet on each day so many people for the time that you're infected, which is K days. And obviously as lambda gets larger, you're meeting more people. As you get smaller, you're meeting less people. Each person you meet, if they're already infected, it makes no difference. If they're recovered, we're going to assume they've had a good immune response, they're safe, they're fine, they're not going to become infected again. But if they are susceptible, there is a probability gamma of them becoming infected. And then they've got K days to each day go out and meet so many people and spread it all on. So that's the setup. So let's go to our studio and look at my code. So this again is in our Markdown. And first of all, I'm going to write a function called sim outbreak, which is this whole thing here. So it's a function name, and it takes altogether 1, 2, 3, 4, 5 arguments. The first of all is how many people in my population. Lambda is the rate that you meet people every day you're infected. Infection probabilities are gamma. It's the probability you infect someone in an encounter. We're going to look for so many days, and K is how many days you're infected once you've got disease. So let's see how I've set this up. First of all, I start with a nice little tibble. So I have a column which is an ID for each person. They just have a number from 1 to however many. They all start susceptible. I'm also going to record the day you're infected and the day you're recovered. And the first thing we're doing is start outbreak by taking the first person and make them infected. They're infected on day 0 and they're going to recover on day K. Now we have this big loop that goes all the way down to about here, which is for every day. And for every day, first of all, I find how many people we have infected. And if there is no one infected, stop, that's it. Then what I do is for each infected person, first of all, they decide how many meetings to have. So here's our first simulation. We're going to randomly choose from a Poisson. We're going to have one random number from that Poisson with the rate lambda equals lambda. Then that's going to be the number of meetings they do for each meeting. They're going to randomly choose people from the population. They choose that person. If they're susceptible, I'm going to take a uniform from 0, 1, because if you think about it, each encounter is a Bernoulli random variable. So if you're susceptible, what I do is I toss like a weighted coin. I get a U, a number between 0 and 1. And if that number is less than or equal to the infection probability, you become infected. If not, you were very lucky, that encounter you didn't do. If you become infected, I set the day you're infected is today, the day you recover is in K days time, and then I just keep doing that for every single meeting, and then we go back. Next thing I do is I look and I say, right, anyone who basically has been on K, we're going to take them from I to R for recovered. So there's my function. We're going to set a seed so you can try it at home and get reproducible. And we're going to do an outbreak where we're going to have 10 people. We're going to have the 3 is the lambda. So on average, they meet 3 people a day while they're infected. There's about a 0.3 chance of spreading it. We're going to look at 10 days and you're ill or infectious for 5 days. So if we run that, here we go. Here's the first person infected. And here you can see, for example, the person number 6 is infected on day 2, recovered by day 7. Okay. All good. Let's have a visualization. So what I've done here is I've just used ggplot to plot that data. As you can see, here is the first person to infect it on day 0, and they are infectious for till day 5. And then I think the next person was day 8, etc. So each of these is, the line indicates the time that someone was infected. In this case, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9. Everyone ended up getting infected in this population. What I'm going to do is I'm going to make myself a nice little function to make this a bit nicer. All it does is it orders them, so we can see the sort of as people get infected. And we can see in this case that our infection went to that point there. So now that looks pretty good. Let's do something bigger. Let's have 100 people. This time they don't go out as much. They only, on average, meet one person. There's a 0.3 chance. We're going to look at it for 40 days. And once you're infectious for 5 days. Have a look at that. And now we can see our outbreak. We can see as people move, they recover, but other people spread it on. Interestingly, this stopped at day 25. Our last person was infectious until day 25, a lot shorter than the 40 days that we were looking at. I'm also getting into something. I'd be interested at the end of this to say, well, a couple of things. First of all, how many people, what proportion were infected in the population? What recovered, what's still susceptible, i.e. they never got the disease. And also what we're going to do is we're going to look at how long this outbreak takes. So here's my little summary. So for example, in this one, we found at the end of it, 98% of the people had recovered. On that last day, we still had a 1% infectious person. Duration, it lasted 25 days. So there's that one person out of the 100 left over. So what I want to do now is I want to go, well, let's try different social distancing. So different social distancing will affect your lambda. When we have severe social distancing, people stayed at home, the rate of you meeting people will be really low, so lambda will be low. While if you're going out, you're ignoring social distancing, you're meeting people, you're going to have a lambda that's really high. So what I want to do is for each lambda, I want to do numerous runs. So what I'm going to do is I'm going to take a lambda and I'm going to do lots of runs. Instead of just doing one outbreak, in fact, I'm going to do lots of outbreaks. I'm basically going to do 100 outbreaks. And for each of them outbreaks, I'm going to get what proportion, how long it lasted, what proportion were infected, what proportion recovered, what proportion is still susceptible at the end of so many days. So all this function does is a little wrapper function that just reruns it numerous times. So if I run this, you can see here's the first outbreak. In this case, lambda's 1. It lasted 13 days. In the end, 30% have recovered, 60% were still susceptible, and 1% were still infected. And we've done all together, you can see it goes 90 more rows, 100 of them. So now what I'm going to do is I'm going to try lambda 1, 3, 5, 10, 15, 20. And this little bit of leak code here just basically runs that simulation each time and puts it all together. And the thing I'm interested in is how many of total infections were there. So that's going to be infections plus recovered or just 1 minus susceptible. I'm not going to run this. This takes time. I've already run it beforehand. But if we have a quick look at it, if I go sims, you can see we've got altogether 600 more rows. We've got 100 for each lambda, and we can see the effects. So now let's look at the behavior. So before I do that, stop and have a think. As lambda goes up, do you in fact expect more or less people getting infected? But the other question is, how does it affect the length of the outbreak as well? Okay, got a pause, had a think, good. Let's have a look. So what we're going to do is we're going to put lambda on the x-axis, the duration on the y-axis, and we're going to just move the points because you'll get a lot of points that all sit on top of one another. So geom_jitter just spreads them out so you can see them. So let's zoom in and look. So what we're seeing here, is it what you expected? First of all, there's a lot of noise. You can see we've added that jitter, so we get all these points spread out. But what you notice is as lambda increases, first of all, the duration increases. Because initially, if you think about it, and we'll check this with other plots, if you are doing strict social distancing, you're not going out there. The disease dies out really quickly because luckily not many people get infected. Then as you increase your lambda, you get to sort of an average, you're meeting 5 people. You can see here, we're getting a long duration. It's sort of ticking over. You're infected enough to just keep them going in that, remember that step sort of function before, that just ticking over. But now when you do lots of social distancing, the length of the outbreak is quite short. But why is it quite short? What's happening in this behavior? Well, let's investigate further. Next thing I'm going to look at is look at the total number of infection. And what you notice here is, again, as lambda increases, you see the total proportion of the population that end up getting infected ends up being such that everyone's getting infected. So you've definitely got this thing as your numbers increase, which makes sense. If you're going out there and you're spreading the disease, the chances are the whole population ends up being infected. Assume in this model, I haven't taken into account things like the fact that people can have natural immunity, etc. I'm going to put that together now. First of all, we're going to produce this plot, and all I've done here is we've now got our total infections on this one. So this is in no one gets infected all the way to everyone gets infected. On here we've got the duration, and what we see is that you've got this increase and then a decrease, because what's happening, if you think about when people are going out and they're doing lots and lots of, so here's a lambda of 20, lots of going out and meeting everyone, the reason the outbreak is so fast is it spreads through the population really quickly. Spreads through and everyone gets hit really quickly, everyone recovers quite quickly, bang, the infection gets over. But the disadvantage is everyone ends up with the disease. And in this case, this disease, we just assume it's a nice disease, it doesn't have consequences of damage to your long-term health or even death. But if this was, other diseases which has a high mortality rate, well, this would be terrible because now the whole population has it. And if you had a mortality of even just 1%, that's a huge number of people passing away. Let's split that up and just reconfirm that with some facet wrapping. So here we've now got the different lambdas. And as we find, when lambda's slow, generally it dies off quite quickly. Not a lot of people get it. Towards the left, so not a lot of people are getting the disease. As lambda increases, we see that more and more people, by the time we get to a lambda of 10, so if you're social distancing this model, on average you're meeting 10 people a day, everyone's going to end up with that disease. But because you're moving out and everyone's getting it, they recover quickly, so you find that the duration goes down. So that's a quick example of just taking a very simple simulation model. I mean, proper simulation models for diseases are much more complicated than this, but it was a nice simple illustration of the simulation stuff that we've done. Simulating that and having a quick play with different social distancing this and seeing the effect on what it does in the outbreaks. Okay, next lecture we will start doing bivariate distributions. See you next time.